Hello everyone. Today we're going to be going over an example problem that pertains to utilizing the Bernoulli's equation. So here we have an example problem in which we have a very large reservoir of water, at the very bottom of our reservoir of water we have a pipe attached to it. Midway along our pipe we have a manometer attached so we can determine the pressure just below our manometer. As per usual, I've gone ahead and listed all of the known values that we have, as well as the assumptions that we're going to be making in this problem. Since we're going to be utilizing the Bernoulli's equation, we have to make sure that we abide by all of the assumptions that were made in the derivation of the Bernoulli's equation to be able to utilize it. So we have to assume 2D, along a streamline, steady, incompressible, and inviscid. So the first part of the problem asks us to solve for V dot. So what is the volumetric flow rate of our fluid flow going through the pipe? Okay. So first off, we have to establish our streamline. So the streamline that we're going to follow to help us determine what V dot is. So what I'm going to do is I'm going to say that the initial point over the streamline that we're going to follow is going to be at the surface of the water within our reservoir. Then, let's say we follow a streamline through the tube, so perfectly in the center of our pipe, and ends just at the exit of our pipe. So it ends just at the exit right here. Okay. So let's go ahead and establish this as point 1. We have our flow direction. And this is going to be point number 2. Now the primary reason, well there's actually 2 primary reasons why I selected this as being our streamline. Because at points 1 and 2, they're both open to atmospheric conditions, which means that when we solve this in gauge pressure, we know that P1 and P2 are just going to be 0 in gauge, since they're both open to the atmosphere. Another reason is that since we have a very large reservoir, and we've said that the initial point 1 is at the very top of our reservoir, we can make the assumption that our reservoir is incredibly large in comparison to any of the flow going through our pipe, which means that we can assume that V1 is about equal to 0. Another reason that's really nice is that we also know that using this streamline we can solve for V2, which we can go ahead and apply the definition of a volumetric flow rate to go ahead and solve for the volumetric flow rate. So overall it's just a very a simple streamline to follow, mainly because we have a lot of things in our Bernoulli's equation that we can neglect just because of how we selected our streamline. Okay, so let's go ahead and write down Bernoulli's equation for our streamline. So we got P1 plus 1/2 rho V1 squared plus rho G Z1, which is equal to P2 plus 1/2 rho V2 squared plus rho G Z2. So as I said before, since we're open to atmospheric conditions, both P1 and P2 are 0 in gauge pressure. So 0 in gauge. Also, we can also go ahead and assume that V1 is about equal to 0 because we're assuming that we have an incredibly large reservoir of water. So this is about equal to 0. So let's go ahead and solve our equation for V2. So we have rho G Z1 is equal to 1/2 rho V2 squared plus rho G Z2. All of our densities cancel out. And in solving for V2, we get the square root of 2 times gravity times the difference Z1 minus Z2. Okay. Now, Z1 minus Z2, we have to go back up here. The difference between 1 and 2 in terms of its depth is going to be our depth d minus 1/2 the diameter of our pipe, so dt, which will bring us just in line with our streamline. So we know that our z1 minus z2 is going to be d minus dt divided by 2. So what we end up getting is that we get v2 is equal to square root of 2 times gravity times d minus dt divided by 2. Now all of these values are known, and if we go ahead and plug these in, just to make the length of the video a little bit shorter, since this is actually a very long example problem, I'm going to leave plugging in the actual known values as an exercise for you guys, but the answer that you end up getting is 8.81 meters per second for our velocity at 2. So now we know the velocity at our point 2, and now we can go ahead and apply the definition of our volumetric flow rate to find the volumetric flow rate throughout our pipe. So step number 2, V dot. So V dot is equal to V dot is equal to our velocity at 2 times the area at 2. Now just one quick note here. I did not put V dot sub 2, and here I'm kind of skipping a step. By conservation of mass, if you were to apply it, you would end up seeing that if you were to apply conservation of mass throughout our pipe, you'd end up seeing that the volumetric flow rate is constant throughout our entire pipe because we have constant density. So we have an incompressible substance, density doesn't change, and therefore throughout our entire pipe the volumetric flow rate has to be the same as well. So this is just me kind of just applying that knowledge directly. But how you'd solve for that would be using conservation of mass. Okay, so we have both velocity at 2, and we also have the diameter of our exiting area. So since the region in which the fluid flow is going out of our exit is going through a cross-sectional area that is represented as a circle, we can replace A2 with pi over 4 times the diameter of our exit squared. Okay, now we can go ahead and say that V dot, when we plug in all of our known values, is equal to 0.069 cubic meter per second. Okay, and that is our final answer for part 1. So we now have the volumetric flow rate for our fluid flow as it's going through the pipe, which remains constant throughout the pipe because we have constant density. Okay, so part B. Part B is going to be a little bit of a longer part, but what it asks us, I'm having trouble speaking. What it asks us is, what is H? So if we go back to our figure, we can remember that H is going to be the difference in our gauge fluid and our manometer, which is taken to be mercury, as given in our knowns. So, actually, let me go ahead and make a note for that. So this is mercury. So what we want to find out is, what is H? Okay, so we actually have a lot of options here in terms of how to select our streamline in order to solve for this. The streamline that I'm going to select is going to go from just below our manometer, so we can use our manometer to find the pressure at that point. So we're going to call that point 3. And I'm going to also apply the Bernoulli's equation just to the streamline between 2 and 3. the reason why I'm selecting this as opposed to, let's say, 1 and 3, which would yield the same answer, is that I feel like it simplifies the problem a little bit more, mainly because we do not have to account for hydrostatic pressure since the streamline is at the same height. And not only that, but we have it open to the atmosphere, which means we can neglect pressure as well. The static pressure, since it's for the static pressure at point 2 because it's open to atmospheric conditions. Now, if we were to select points 1 to 3, we would have to account for hydrostatic pressure, but we'd also be able to neglect the velocity at 1, and I think that's about it. Oh, and we'd be able to also neglect the static pressure at that point as well, because it would be open to atmospheric conditions. So I feel both will yield the same result. So it's completely up to you as to which one you want to select. I just feel like going from 2 to 3 simplifies it a little bit more, mainly because we don't have to account for the hydrostatic pressure. But again, both will yield the exact same result. Okay, so let's go ahead and apply Bernoulli's equation between points 2 and 3. So we have step 1. So we're going to go from 2 to 3 for Bernoulli's equation. So you get P2 plus 1/2 rho V2 squared plus rho G Z2 is equal to P3 plus 1/2 rho V3 squared. So we have 1/2 rho V3 squared plus rho G Z3. Okay, since our streamline is along the same height, our hydrostatic pressure terms can go away. At P2, our pressure is open to atmospheric conditions, so this just goes to 0 gauge. And what we're left with is 1/2 rho V2 squared, which is equal to P3 plus 1/2 rho V3 squared. So let's go ahead and solve this for P3. So we get P3 is equal to 1/2 rho V2 squared minus V3 squared. So we now have the pressure at point 3 by means of solving it using Bernoulli's equation. So now what we can do is, if we go back up here, the point that we selected is just below the manometer, which means that we can use our pressure variation with depth equations to solve for what the pressure at 3 is via our manometer. And in doing so, we can equate the equation that we get by solving the manometer part to so in solving the manometer part that we have for the pressure at P3, and equate that to the pressure P3 that we found using Bernoulli's equation, and then therefore solve for H in that means. So essentially, to simplify my words, because I think I made that sound a little bit more complicated than necessary, is that we found P3 via Bernoulli's equation, and now we're going to find P3 via our pressure variation with depth equations by means of looking at the manometer. Okay. So there's actually one more step that I would like to do, though, before going into solving our manometer problem, and that is we don't know what V3 is. So that's kind of a problem at this point. But it's a very simple problem to fix, because what we can do is since we have a partially confined flow, we're just going to go ahead and use conservation of mass. So conservation of mass will help here. Now, just a quick note, the flow does not have to be confined or partially confined to use conservation of mass. Conservation of mass it must be abided by all time, at all times. But in general, when you see confined or partially confined problems in Bernoulli where you want to use Bernoulli's equation, you will pretty much always have to use conservation of mass to figure out something in there, generally a velocity or a volumetric flow rate. So that's all I meant by that, is that in general, when you have a constrained flow, you'll have to use conservation of mass at some point. Okay, so we have dmCv dt is equal to m dot inlet minus m dot exit. So we have to assume steady, and this just comes from the assumption list that we had listed above. And we get m dot 2 is equal to m dot 3. So now let's go ahead and apply our full definition for the mass flow rate to both points 2 and 3. So we have rho v2 a2 is equal to rho v3 a3. We have an incompressible substance, so our densities will cancel out since we have constant density. And we can solve for v3, which is just going to be v2 times the ratio of our areas. Now we can say, so by plugging in our area for the cross-sectional area of our pipe, so it will be just the area for our circle, we can plug in pi divided by 4 times the diameter squared for both points 2 and 3. So at point 2 will be the exit area, point 3 will be the tube area, which have different diameters, and what we end up seeing is that we get dE squared divided by dt squared. So when we go ahead and plug in our values for this, we get that V3 is equal to 13.76 meter per second. Okay. So that is our velocity at point 3. So since we have the velocity at point 3, point 2, as well as the density, now using the expression that we derived using Bernoulli's equation, we now have the pressure at 3. So let's go ahead and apply our variation of pressure with depth equations in solving the manometer part for P3 as well. So we can relate that pressure at 3 to our difference in our gauge fluid height h. Okay, so step 3. So we're going to be looking at some pressure differences here, so let's go ahead and establish points. So we're going to go from point 3 to the very top of our gauge fluid here, which we're going to denote as A. Then we're going to go from the very top of our gauge fluid here to the lower portion of our gauge fluid, which is open to atmospheric conditions here. And we will go ahead and denote this as point B. Okay, so let's go ahead and now find the pressure differences between points 3 and A and B, and then solve that for the pressure at 3 so we can find out what H is. Okay, so let's go from 3 to A. So what we end up getting is that P3 minus PA is going to be equal to rho G, and if we go back up to our figure here, the difference between point 3 and point A is going to be H1 plus dt divided by 2. Okay, so let's go ahead and write that down. So we get H1 plus dt divided by 2. So now let's go from A to B. And we have PB minus PA is equal to rho of mercury times gravity times our height h. So the difference in height between our gauge fluid. Now recall that at point B it's actually open to atmospheric conditions. So this term will actually just go to 0 because we'll solve this in gauge. And what this tells us is that the pressure at A is just equal to minus the density of mercury times gravity times height. Okay. So now what we can do is we can take this expression and plug it into our expression up here for P3 minus PA. So what we end up getting is P3 plus rho hg times gravity times height is equal to rho g h1 plus dt divided by 2. Now we can go ahead and solve this for P3. So we get P3 is equal to rho g h1 plus dt divided by 2 minus rho hg times gravity times height. Okay, cool. So now we have P3 via solving our manometer problem. So now what we can do is we can just equate the P3 that we found via our Bernoulli's equation with the P3 that we found in solving the manometer and solve that for H, and we have our end result. So let's go ahead and do that. So then we have P3 is equal to 1/2 rho V2 squared minus V3 squared is equal to rho g h1 plus dt divided by 2 minus the density of mercury times gravity times height. So in solving our expression here for H, what we end up getting is H is equal to rho g h1 plus dt divided by 2 minus 1/2 rho V2 squared minus V3 squared, all divided by the density of mercury times gravity. So all of these values we now know. So what we can do now is just plug in our known values, and what we end up getting for our height, so our difference in height for our gauge fluid in the manometer is 0.565 meter. And that is our final answer for part B. So lengthy problem. But it's a very interesting problem. Not only that, but it also shows the importance of selecting your streamlines. Now, this solution, so with Bernoulli's equation type problems, there are numerous solutions because you can select numerous types of streamlines to follow. So, for example, we solved a problem going from 1 to 2 and then 2 to 3. You could have also solved the problem going from 1 to 3 to 2. That one would have been a little bit more difficult, mainly because you wouldn't have been able to solve for too much at point 3 because you don't know what H is. But it is another way of solving it. You could have also gone from 1 to 2 and then 1 to 3 and solve the problem in the same way. So there are 3 solutions that I can see just straight off the bat that would yield the exact same answer. And most of the problems are like this. But in general, I try to aim to go for the path of least resistance. So where can I make the best assumptions to reduce the amount of algebra and work that I have to do to still get the correct answer. So hopefully this video was helpful. If you have any questions regarding any of the assumptions that we've made or any of the selection process of the streamlines or anything like that, feel free to ask me in either lecture or leave a comment below in the comment section. Again, I hope this was helpful. Thank you for watching, and I will see you next time.